using colligative properties and osmotic pressure to do molar mass calculations. So there are just a couple of different ways in which you will be seeing this, and so we're going to be going over all of them. So example A is if you have a non-ionic solute that is dissolved in 4 kilograms, 0.4 kilograms of distilled water, if 27.36 grams results in a freezing point depression of negative 1.444 degrees Celsius, what is the molar mass of the compound? So non-ionic means that there's no Van 't Hoff factor, or the Van 't Hoff factor is equal to 1. The normal freezing point of water is 0 degrees Celsius, and my delta T is 1.444. So I'm just going to plug that into my equation. Delta T is equal to Kf m, and the Kf of water is 1.86 degrees Celsius per molality. I'll solve for the molality of my solution. So my molality of my solution that will result in a 1.444 degree decrease in freezing point is a 0.7763 molal solution. So I don't have 1 kilogram of water, I only have 0.4 kilograms of water. So I just do the ratio to find out how many moles that would be. So rather than 0.7763, it's 0.3105 moles. And that 0.3105 moles represents 27.36 grams. So then I just divide grams by moles to get my molar mass. So my molar mass would be 88.16 grams per mole. Got 4 sig figs. This really should be 0.4000, 4 sig figs. Example B is if I have a Van 't Hoff factor. Okay, so if I have an ionic compound with a Van 't Hoff factor of 3, and it's dissolved in 800 milliliters of water at H2O at 52 degrees Celsius, if 52.9 grams causes the vapor pressure to lower from 102.1 torr to 99.0 torr, what is the molar mass? Density of water at 52 degrees Celsius is 0.987 grams per milliliter. So I first need to figure out what my mass of water is, because I am using, and how many moles I have. So I have my mass, and my mass of my water is going to be 0.987 grams per milliliter times 800 milliliters, and then I divide by the molar mass to find out how many moles of water. I need to find out moles of water and moles of solute, because remember that when I use vapor pressure lowering, I use the mole fraction. Because of the Van 't Hoff factor, the moles of solute is going to be 3 times the moles of my ionic compound. So I'm actually going to put in 3x for my moles of dissolved ions. So my new pressure is going to be equal to my moles of my solvent over total moles times the original pressure. So my new pressure is going to be 99.00, and I'm going to have my moles of water be 43.87, and my total is 43.87 plus 36. I don't know what that moles of my ionic compound are, times the original pressure. So I solve for x, and my x ends up being 0.458 moles. And that's the moles of ionic compound that I put in, not the moles of ions that have dissolved. So then, now that I have 0.458 moles, which represents 52.9 grams, I divide grams by moles to get the molar mass of 115.5 grams per mole. So that's where I have a Van 't Hoff factor. You could have done that problem by doing the change in pressure is equal to the mole fraction of my solute over my thing, but then I would have 3x over 43.87 plus 3x. So in that case, rather than having an x value in both places right here, I used the new mole fraction, just used the mole fraction of my solvent instead. So you always have those options. Use the option that makes your math calculation easier. And the final one is osmotic pressure. So in those cases, I was using molality for boiling point elevation or freezing point depression, mole fraction for my vapor pressure lowering, and in osmotic pressure, I'm using molarity. So here's an example in which I have a 0.97 grams per liter of a non-ionic compound. So again, no Van 't Hoff factor. The osmotic pressure is 0.0828 atmospheres at 25 degrees Celsius. What is the molar mass? So I plug everything in to find my molarity. And then I have that equal to 0.97 grams per liter. And then I solve for grams per mole, and then I get my molar mass, which is 287 grams per mole. So in each of the cases, at least with osmotic pressure and the colligative properties, not VPL, just boiling point, elevation, and freezing point depression, you're usually going to be solving for either molarity or molality.